This third screencast will finish off on information on the nerve action potential that we started in Screencast 2, and we'll talk a little bit about myelin as well, the substance that wraps around axons and speeds up the potentiation and the conduction of the nerve action potential. This is really just a slightly different diagram to the one that I've shown you previously, and it really just kind of highlights the importance of sodium, Na+, and potassium, K+, in the derivation of the nerve action potential. So essentially this term here, G, stands for conductance. So Gna is the conductance of sodium, Gk is the conductance of potassium. So Gna shown, conductance of sodium shown in black. You get a rapid rise in sodium, and then the sodium channels, as we'll see over the next couple of slides, close very quickly over the order of a millisecond, whereas potassium tends to switch on more slowly and switch off slightly slower as well. This inward phase is largely due to the increased conduction of sodium. This hyperpolarizing phase is due to the opening of a potassium channel. Maybe importantly, sodium is an inward current because of the concentration gradient that I showed you on one of those previous slides. Potassium is an outward hyperpolarizing current because the concentration of potassium is higher inside the cell to outside the cell. And again, this maybe looks like a slightly complicated diagram, but hopefully isn't. Really just to concentrate on here, these show you different what we call gates, which control the movement of both sodium and potassium across the membrane. So this column here is the sodium channel, this column here is a potassium channel. And this idea of a channel is just an opening in the membrane that lets either sodium into the cell down its concentration gradient, or potassium out of the cell, again down its concentration gradient, because potassium is higher inside than outside, sodium is higher outside than inside. And this is again our nerve action potential, and what I really want to do is just show you how these gates control the movement of sodium or potassium across the cell membrane. So in state A, which corresponds here, this is B, C, and D. In state A, essentially what happens is both the sodium ion channel and the potassium ion channel are both closed. So the gates are shut. So there's no movement of sodium, no movement of potassium, and we're sitting around about -70 for the reasons that I told you about in screencast number 2. During depolarization, B, shown here, what happens is the sodium channel opens, sodium comes from outside the cell to inside the cell. And again, if this is a little slightly confusing, remember that the cell inside of the cell is around about -70. So as more and more positive charge comes in, we get this depolarizing phase, more and more positive. So it goes from being a minus number towards a positive number. As we said on those previous slides, previous screencasts, you typically round about +50 when all of the sodium has come inside the cell. At this time, the potassium channel is still shut, the same as it is at rest. What happens during this repolarizing, or sometimes called hyperpolarizing phase in C, is that the sodium channel shuts and the potassium channel opens. So now what's happening is we're going lots and lots of positive charge is actually leaving the cell. So we go from this positive value up here back down towards this negative value. And because the potassium moves quite slowly, as I showed you on that previous slide, we tend to get this what's called an undershoot, where not only do we go back to the resting potential, but we go slightly under the resting potential. And again, that's shown in D, and that's really basically because the sodium channel has fully shut, if you like, and the potassium channel is taking a little bit of time to close. So take home message, this action potential can be looked upon as being dictated by the movement of sodium in B, and potassium in C, and to some extent D, through these different ion channels controlled by gates. And this is just for completeness, really. If you want to know more information, the activation gate for sodium is called an M gate. The inactivation is called an H gate. For potassium, the activation gate is called the N gate. You might see these terms in textbooks, again, really just for your information. So again, this is important just to spend a little bit of time on this. Because the action potential either fires or doesn't fire, as long as it reaches that threshold, all action potentials look the same. So we'll see that there are other types of potential that can look different. Specifically, the excitatory postsynaptic potential or the inhibitory postsynaptic potential. We'll come on to those in the next set of screencasts. But essentially, every action potential has the same format. So when we draw a picture of an action potential, it always looks like this, and you'll see that this this waveform is consistent through all of the previous diagrams that I've shown you on these screencasts. And that's because an action potential is said to be all or nothing. Action potentials have similar magnitude, size, and duration, around about a millisecond, and they either fire and reach a similar magnitude and duration, or don't fire, and then they're not an action potential anyway. So action potential is said to be all or nothing. A couple of other, again, maybe things that you'll see in textbooks and are important to know about as you go through the rest of the course. There's a period called the absolute refractory period, and the ARP, absolute refractory period, is shown here in red. And this period means that an action potential absolutely cannot fire again, basically because the sodium channel is open or inactivated, cannot be reopened. You can't fire another action potential during this red phase. Conversely, there's this yellow phase called the relative refractory period. In this period, it is possible to fire another action potential if you put a lot of stimuli into the system. So basically, because potassium channels take a little bit longer to shut, then normally during this period we can't get an action potential. It's called the relative refractory period, so we can't fire another action potential. But if we put stimuli into the system, we can force the sodium channel out of its inactivated state and allow it to open again. So again, really just for completeness, you might hear about the absolute refractory period and the relative refractory period later on in the course. In terms of action potential propagation, movement, essentially the sodium channels and potassium channels are concentrated here in this region called the axon hillock. Again, sometimes called in some textbooks the axon initial segment. So the action potential arises here. What happens is then that the action potential is propagated down the axon to these terminal branches and also to these axon collaterals in certain situations. What is important for the rest of this screencast is just to consider the actions of this myelin. So myelin is a substance which wraps around the axon, and where there are gaps in the myelin is at these nodes of Ranvier. And we'll see at these nodes of Ranvier there's a high concentration of sodium channels, which allows us to generate an action potential in these areas as well as down here at the axon hillock. So let's consider myelin in a little bit more detail and its properties. So take-home message, myelin determines what we call the conduction velocity, how fast the action potential is conducted down the axon. Two different types of cells are responsible for the myelination. In the central nervous system, but maybe we said back in screencast number 1 or 2, oligodendrocytes, these non-neuronal cells, are responsible for myelinating the axon. In the peripheral nervous system, which we'll talk about, like I said in the later screencasts, there's a specialist type of cell called a Schwann cell, which myelinates the axon. And hopefully this becomes a little bit clearer in these diagrams. This is an example of a Schwann cell. which forms myelin, wraps around the axon. Here's the nodes of ROM-VA again. If we were to look at that in cross section, we can see that the axon is in the center here, and this spiral output, if you like, from the Schwann cell wraps around and around and around the axon in order to myelinate it. So it wraps around it, myelinates it, or insulates it. Much like maybe if you have an electrical wire with a plug on the end of it, you'll have a insulating wire or an insulating covering around your electrical wire. So think of the axon as the wire in the center, and this is the insulating covering, which allows electricity to flow much quicker than if you had a bare wire, for example. So again, from an electrical point of view, the way that myelin works, it decreases what we call the capacitance, and a capacitor is just something that stores charge. So myelin decreases the capacitance of an axon and restricts the generation of the axon potentials to the nodes of ROM-VA that we showed you on that previous diagram. Action potentials conduct with little decrement, which means they don't decrease in height, they're all or nothing, and at great speed from one node of ROM-VA to the next. And this is just a diagram maybe to show you the speed of conduction and how it's different between mammals and maybe lower life forms, something like the squid. So if you look at the diagram of the diameter of a myelinated axon of a cat, shown here in red, narrow diameter, but as we increase the diameter, the conduction velocity increases. So essentially what this is telling us is as we get more and more myelination, the diameter gets wider and we get faster and faster conduction. Important to show or to point out that in an unmyelinated axon, again, we see this increase in conduction velocity as they get wider and wider, but the diameter here is much higher. So, you know, around about 100 times higher in this unmyelinated axon. Despite that, the fact that it's unmyelinated, doesn't have myelin, means that the conduction velocity can never get as high as that in a higher animal like a cat, like you and I. And so essentially the take-home message is that higher mammals can communicate much more effectively, much quicker, if you like, than lower life forms, things like a squid. We'll consider some of these other fibers as we go on to talk about things like muscles and pain later on in the course. But again, the take-home message here is that there are a set of different fibers that have a different amount of myelination. So highly myelinated fibers, things like A alpha fibers, thickly myelinated, have a much higher conduction velocity, can communicate much quicker with each other, if you like, than unmyelinated axons, things like C fibers, which are involved in pain perception. And again, that just corresponds with the diameter. So the more myelin you have, the wider the diameter of the myelinated axon, the faster the conduction velocity. Myelination determines conduction velocity. Again, maybe just this reference diagram. Again, you can see the myelin sheath here, just for reference, and these nodes of ROM-VA where we can generate other action potentials. Again, we'll talk about these probably in other parts of the course. So why is this important? And maybe from a medical point of view, let's just finish off the last couple of slides and talk about a disease where myelination breaks down. So maybe you've heard about multiple sclerosis. It's an important central nervous system disease thought to involve the destruction of myelin and thought to be what we call an autoimmune disease, or an autoimmune disorder. So an autoimmune disorder, autoimmune disease, in this case, it's when the body actually produces antibodies against a protein or a substance within the body itself. So you get an immune reaction against your myelin. Myelin is destroyed, and what happens due to that is a disease called multiple sclerosis. Onset of multiple sclerosis, MS more commonly called, typically around about 20 to 40-year-olds, affecting a large number of people worldwide. Around about 2.5 million people suffer from multiple sclerosis. And the reason that we get multiple sclerosis is, or the way that we can detect multiple sclerosis is again using imaging, which we talked about back in the first screencast. So if we take a MRI scan of somebody with multiple sclerosis, what is obvious from the scan that shouldn't be seen in a healthy person are these white areas here. And these white areas are called plaques or sclerotic lesions. And that's where you get the name multiple sclerosis. So if you have a lot of these sclerotic plaques or sclerotic lesions, you have multiple sclerosis, multiple plaques. And essentially what happens is that your myelin has broken down. The nerves within these areas of the brain can't communicate properly, and you suffer this neuromuscular disease, multiple sclerosis. So that's a good place to finish. I'll just talk you through this very quickly, but you can pause the screencast and read it for yourself as well. We now know that neurons, which are the functional units of the nervous system, signal by action potentials. We have had a resting membrane potential, which is dictated predominantly by potassium and chloride in the mammalian nervous system, and that's due to the fact that we've evolved so that we set our resting membrane potential round about -70 millivolts, and potassium and chloride have useful equilibrium potentials in order to generate that resting potential. Action potentials are rapid, they're all or nothing, and they're generated at this area called the axon hillock. They're initiated by a rapid increase in sodium permeability, causing that depolarizing phase, and a slower increase in potassium permeability, which repolarizes the membrane. Two terms which you should be aware of: absolute refractory period, where you absolutely cannot generate another action potential, and the relative refractory period. What we want to do is we want to space our action potentials. We want consistent periods so that we don't get irregular neuronal firing. In terms of myelin, we've got different types of axons. Large diameter axons conduct faster because they're highly myelinated, so they've got a higher conduction velocity. We haven't talked about saltatory conduction. Again, maybe just for completeness here, saltatory comes from a Latin word, which means to jump. And in some textbooks, you'll see communication between nerves described as saltatory conduction, basically because the action potential can jump from one node of ROM-VA to the other. So if you're wondering what saltatory conduction is, it just means the action potential can jump from one node of ROM-VA to the other. And again, that's because of myelination and the fact that these nodes of ROM-VA express high concentrations of sodium channels. In the CNS, oligodendrocytes are the things that are important for myelination. In the peripheral nervous system, Schwann cells. Action potentials are all or nothing, encoded by firing frequency, which is measured in hertz. Again, these are things that we'll come back to probably later on in the course. This is just for completeness at part 1 level. Okay, so that's a good place to finish screencast 3. In the next set of screencasts, we'll start talking about chemical synapses and some of the neurotransmitters. Again, important information, not only for part 1, but going on into part 2 and 3 later on in your pharmacy degrees.